We've been spending time in the last few weeks introducing a SolidWorks-based design methodology. We're going to stick with that message today and work on designing a mass-produced plastic injection molded part, which is actually going to be the faceplate on this digital receiver box. Oftentimes as designers or analysts, it can be overwhelming the amount of decisions and data that we have to sift through in order to make informed decisions. What we really want to do with this methodology is give you tools to make intelligent design decisions by utilizing simulation-driven product development. Let's talk a little bit about what that might look like in this case. For this design scenario, we're going to need to ensure that our faceplate meets some safety requirements. We're going to shoot for a factor of safety of 4. We also want to minimize weight. We'll be inspecting different plastic materials, so we'll consider the cost of the material as well. We're also very excited to bring to market our new plastic suite of tools that allow us to, really look at the moldability of a part. So for any injection molded parts, whether they're multi-cavity or individual parts, we can really take a deep dive and ensure that our parts are going to be moldable. We can look at things like weld lines, short shot, sink marks, shrinkage, and evaluate all those things with respect to trying to make the best design decision. And finally, we'll look at the environmental effect that these different materials will have. So let's start out with the basic question we're trying to solve. Which material should we use? We can see from this chart that we're going to be investigating 4 different plastics, and we're going to be looking at their cost also. And one of the design variables that we're going to be investigating is actually the thickness of the part. So we're going to vary the thickness, try to ensure that we hit our factor of safety of 4 while minimizing weight, and then we'll analyze exactly how much each of those optimized thickness parts are going to cost to produce. So let me hop out of SolidWorks here and spend a little bit of time in the FEA suite showing you guys how we can do an optimization. So here we've got the actual faceplate. SolidWorks is nice in that it allows us to utilize different configurations, so we can have different configurations that represent the faceplate and with different materials. And then once we've optimized the thickness, we can specify different thicknesses in each of those configurations to then go on and look at the ecological impact as well as the moldability, manufacturability basically. But again, as a starting point for us trying to extract information about this design, let's just look at a standard finite element analysis run. So we're going to start with the ABS material, and you can see that one of the design variables is the shell thickness, and that shell thickness is actually the thickness that we're going to vary in an attempt to get this as close as possible to a factor of safety of 4. The design suites available in SolidWorks Simulation are very, very intuitive and easy to use, but also very, very powerful. So whether you're a designer or an analyst, there's definitely some data that you'll be able to extract in an attempt to make good, solid, informed design decisions. In this case, you can see that we've specified our material as ABS. We've got some fixed boundary conditions basically on the back of that faceplate where it's going to be fixed to the rest of the receiver body. And then on the front of the faceplate, we're just applying a 15-pound force. So basically, we're just pushing this thing with 15 pounds. Now, there's a whole host of data that we can extract, but usually as design engineers, one of the most important things we look at is the stress that load is going to cause on our part. And you can see here we're looking at the stress in that faceplate. It's the yield strength of this material is 6526. We can see that we're we're plotting from 0 to 1,000. And we can take a look at exactly where those high stress points might be. Obviously, we can do things like animate this if we're interested in seeing exactly how this thing is going to deflect. We can look at the displacement if there's a displacement budget that we're trying to achieve. And we can also look at things like factor of safety. Now, once we've run the first finite element analysis, it's very, very easy to just right click and say I want to create what's called a design study. And when we do that, The design study is going to actually allow us to specify how we want to vary geometric or material properties. So in this case, you can see I've set up one variable here for the shell thickness, and I want that shell thickness to vary from 1 millimeter thick to 3.5 millimeters in steps of a quarter millimeter. My constraint is that I want my maximum stress in the areas of interest to be below the yield stress divided by 4. So in this case, it's 1631.5 with a goal of minimizing mass. We set this up, we allow it to run, and then we have all these different scenarios that we can evaluate. So for instance, you can see the first scenario where we have a thickness of 1 millimeter. If I click on it, I can go ahead and see what the stresses look like in that case. We can see that any of the scenarios that are highlighted in red means that it hasn't met our constraint. And we can have constraints that go over multiple design runs, right? In this case, we're really interested in stress, but perhaps you're interested in natural frequency or thermal results, really a whole host of variables that you can, or a whole host of physics that you can solve for and constraints that you can set up. In this case, it tells us that the optimal thickness is 1.75. And in that configuration, we've got a stress of about 1509 on the parts of interest, and our mass is about 52 grams. So we can do that for all of the different plastics, and then we can come back and extract a little bit of information about exactly what mass each of them is going to have in their optimized configured state. And then based on the mass, we can go ahead and, knowing the cost per unit mass, figure out how much it would cost to manufacture, let's say, 1 million of these. So let's go back into the PowerPoint presentation now and take a look at exactly what this type of run, what type of information that can give us. So we've returned now to the PowerPoint presentation. Let's take a look at exactly what those runs have actually yielded for us. And what we can see is that, for any of these materials, there is a thickness that will allow us to reach our factor of safety goal. For polycarbonate, that thickness is going to be 1.25 millimeters, while for an HDPE, a high density polyethylene, it's going to be 2.75 millimeters, and various thicknesses for the other materials. So if we were just going by weight, we'd probably want to pick the one with the thinnest thickness, which would be polycarbonate. But let's do, as our job as design engineers and analysts is to really take all this information and make informed decisions. So when we factor in cost, what we see is that polycarbonate is actually the most expensive to manufacture because of its cost. It would cost us $171,000 to make 1 million of these, whereas polypropylene is only $135,000. So one of those materials in the middle it's going to be actually much, much cheaper. That polycarbonate thickness could give us problems during plastic injection molding, right? So again, we've got one really good point that we can use to make our design decisions. So in this case, the recommendation would probably be to use polypropylene. So let's take a look at some of the things that we've addressed here. We've addressed safety, we've addressed weight, and what I mean by weight is that for each of the different plastics, we've definitely minimized the weight because we've gone through and made sure that the thickness that we've chosen is the optimal thickness. So it's as thin as it can possibly be while still meeting that factor of safety requirement of 4. And then we factored in cost of the material, right? The variability of these, the cost of these different plastics. So we were able to test our designs virtually. We didn't have to make any prototypes. We were able to optimize virtually and minimize the weight. And we were able to take a look at the cost. Now let's move on to manufacturability and look at exactly how we can run some plastic simulations to ensure that all of these designs are moldable and add another point to our design decision criteria. So we're back in SolidWorks now. Let's go ahead and take a look at our newly released plastics tool. So I'm just going to come up here and click on the tab for plastics, and it's got a very basic design tree similar to the simulation tool or our flow tool. We kind of walk through the tree, make our specifications for different things, and that allows us to go ahead and run our simulation. I just want to point out a couple things here. First, let's take a look at the polymer selection menu that's available. And what you can see, right, is we've got a very, very extensive list, over 5,000 polymers available. Obviously, you can create your own, but most likely the polymer that you want to use is going to be defined here. We've also got a whole host of machines that we can specify. We've got relationships with all these different vendors, so chances are your machine, again, is going to be here. But again, if your machine isn't, you can always create your own user-defined. The machine's important because it specifies the injection pressure, and that's one of the things that we really want to monitor. We want to have a low enough injection pressure, probably around 15,000 psi is the cutoff before you need to go from small machines to large machines. It also tells us things like the clamping force and how much material it can push through. We can also specify flow settings, pack settings. One of the nice things we can say exactly where we want our gate to be located. So you can see in this case, we're saying that we want the gate to be back here. We can specify the properties of the gate, so its diameter. SolidWorks Plastic can also tell us exactly where it feels like the optimum gate position would be. And there can be multiple gates. So if you had a part that had a multi-gate injection, we can handle that all the way up to 10 gates. But now let's go ahead and take a look at the results here. So I'm going to start by showing the flow results. That's probably where most people who are doing plastic design are going to start. So the first thing that we notice is it's going to take about 2.4 seconds to fill this thing. If I hit play, we can see basically the flow front that this thing is going to take. I can also click on my results advisor and it's going to give me some information. So it's going to tell us what the maximum injection pressure required to fill this is. It's telling us here that this particular configuration might need some help because we're over 90% of the maximum injection pressure that the machine can put out. Let me go ahead and stop this here, and I'm going to close this. There's a whole host of other information that we've got access to also. For instance, we can look at the shrinkage. So you can see this thing is going to shrink about 9% at the end of the fill. We can look at the cooling time, so it's going to take about 50 seconds for this thing to cool to a point where it's gone through its glass transition, and we can remove it. We can look at things like sink marks. Take a look at exactly where the sink marks are going to be, the depth of the sink marks. We can look at ease of fill, which tells us areas where that are going to require more than 70% of the ejection pressure of the machine is going to show up in yellow, and more than 90%. Or 85% is going to show up in red. We can also look at weld lines. So weld lines are basically places where the flow fronts come together and hit, and they can be areas where you're going to have low strength. Also, on plastic injection molded parts, they could be areas that you're going to have some visual discoloration. So you wouldn't want your weld lines to be places, on cosmetic parts that people are going to be looking at. Finally, we can look at the air traps, right? And air traps tell us exactly where we might have to vent this thing to air in order to avoid air getting, trapped in the part. We also have results that we can look at related to pack. So after fill, we go through some packing. And some of the things that are interesting, we can look at the volume shrinkage at the end of pack. So it's going to be a little bit less because we've shoved more material in there. It's about 5.7% shrinkage. Also the residual stress in the structure, right? Because there's going to be some warpage that this thing goes through as a result of the residual stress. So lots of different information that we can extract from the plastic tool. So let's go back to the presentation now, take a look at exactly what that information yielded for us and how we can use that in making our design decisions. If we take a look at the data, and the data is very interesting in this case, we can see that ABS takes about 2.4 seconds to fill. The pressure required is under that 15,000 psi threshold. The cooling time is about 50 seconds, and that percent shrinkage is about 5.76%. Now, for mass-produced parts, you're going to want to minimize your time, right? So one of the nice things about ABS, as we can see, is it takes about 51 seconds to produce one of these, as opposed to a polypropylene or HDPE, which take over 70 seconds. Now polycarbonate, which was the material with the smallest thickness, was actually not injection moldable using that machine. We actually achieved short shot. We can pretty much eliminate PC from the our material choices. And in this case, I would argue that ABS might be the best material. Now, there are some issues that, depending on your specific design criteria, it might push you to one of the other plastics. For instance, ABS did require a little bit more pressure. Now, if that could be a potential problem for you, then you might want to pick HDPE or PE. Let's go back now to our design criteria. So now we've looked at manufacturability and ensured that our parts were moldable. Next step, let's go ahead and take a look at the ecological impact that these parts are going to cause using our sustainability tool. So back in SolidWorks, I'm just going to activate my sustainability menu or toolbar, and we can see I'm still in the ABS configuration. I can specify where this thing is going to be manufactured, how long it's going to be built to last, the process that this thing is going to, how it's going to be manufactured, the electricity and gas that are used during manufacturing, the percent scrap, where the device is actually going to be used, also the transportation from manufacturing to usage area, and then we can also look at end-of-life concerns. So are things going to be incinerated, recycled, or thrown into a landfill? And we get our carbon footprint, our energy consumption, our air and water pollution. Also nice explanations of exactly what each one of these are. So that's nice, but one of the things that we can also do is I can say, let me just try to find a similar material. So let's say I want to actually look at a plastic that maybe has a similar elastic modulus. And I can go ahead and say find similar. It gives me a few different plastics. I can click on any one of these and it's going to tell me how they rate. So red meaning that they're worse in the individual environmental impact factors. So this particular plastic worse in all 4, this one worse in 1, and then this one better in all 4. So, just more information. Why not have it, right? There's no reason to not do something like this when it's available to us as design engineers. So let's again go back to the PowerPoint and we'll take a look at the data that we've extracted for these 4 different materials that we're investigating. So if we extract the data that we got from our sustainability study and just compare our carbon footprint basically and look at just miles driving an average US car, we can see that polypropylene is the best choice. It would be about 87 miles. ABS and HDPE are both the same at about 100 miles, and polycarbonate is at 140 miles. So for us, the best choice would be polypropylene. So what have we done? We've looked at the ecological impact and basically gauged it for each of those different plastics. So now we can very confidently go into a design review and say, hey, green being the best choices in these different areas. Obviously, any of the plastics with the right thickness can meet our safety. With respect to cost, polypropylene's best. With respect to manufacturability, ABS. Respect to the ecological impact, it's going to be polypropylene. Yellow means they're not the worst, they're not the best, they're in the middle. So you can see where the different materials fit in with respect to that. And then red, polycarbonate should really not be on the list because it's not manufacturable. But just to fill out all the design review dots, we kept it and ran it through the rest of the model, the rest of the design review. We can see exactly where that fits. So in this case, we'd probably say, let's go with polypropylene. So now we can go ahead and make our suggestion and move this part into, the secondary stages where maybe a prototype is going to be built. We've evaluated multiple options, all virtually, didn't require us generating any prototypes, and we've made very, very informed design decisions, which is responsible engineers and designers. That's really what our job is. And we can see, right, we've done a good job of taking, a scattering of points and using a really clear design methodology to arrive at the best decision. And that's really the goal here that we're trying to do with SolidWorks, right? We want to give designers and engineers the tools necessary to make accurate and intelligent design decisions. So that ends this particular topic. We're going to be producing more of these in the coming weeks and months, and we hope that this was helpful for you guys. Thank you for listening.